Okay, we're going to pick up where we left off from the notes in class, right? So we're going on to number 2 here, a speeding bullet. So a bullet fired straight up from the moon's surface would reach a height of s equals 832 t minus 2.6 t squared feet after t seconds. Again, remember that when we're talking about position and velocity and acceleration, s of t is usually where it denotes the position of the object. So it's the height of the object, right? On Earth, in the absence of air, its height would be s equals 832 t minus 16 t squared feet after t seconds. How long will it take for the bullet to get back to the ground in each case? So when is the bullet coming back to the ground, right? So we're looking at when s equals 0, because when the bullet comes back to the ground, the height is 0, right? So in this case, you actually are not required to do any calculus. This is pure algebra. So you're really looking for the one for the moon, which is this one right here. When does it equal 0? When is height equals 0? That's when it hits the ground. So initially it's 0 and it shoots up because you're firing the bullet. And then when does it come down? That's when the height is 0 again. And then same thing for the Earth. You're going to take this equation and set it equals 0 as well. Okay. All right. So the first equation for the moon, we get 0 equals 832t minus 2.6 t squared. You should use a calculator to help you because I don't expect you to do this by hand. This factoring is not super obvious. So, okay. So we're going to just go ahead and factor out t because they both share t. So 0 equals t, 832 minus 2.6 t, right? So of course we set that t equals 0. That's your very initial when you first start firing the bullet, t equals 0. And then the second will be 832 minus 2.6 t equals 0. That's 832 equals 2.6 t. T is 832 divided by 2.6. T is 320 seconds. So on the moon, because the gravity is definitely less than the Earth, so then it's going to take longer for the bullet to fire up and then come back down. It's going to take 320 seconds, about 5 minutes, right? According to this equation. I don't know how true this equation is, but according to this equation. All right, on Earth, we're going to use the other equation. 0 equals 832t minus 16t squared. Same as before, it's easier to just factor out the t, 832 minus 16t. So t equals 0. Again, that makes sense because initially when we fire the bullet, it's at 0. And then 832 minus 16t equals 0. 832 equals 16t. 832 divided by 16. It is going to take 52 seconds on Earth. And, again, realistically, again, I don't know how realistic this is, but we do know that on Earth, there's more gravity. So it's going to pull the bullet down faster. So it's going to take less time. Okay. All right. So the problem is missing the first word. So I'm not sure why, but the graph shows the position of s of t of a particle moving along the horizontal coordinate axis. When is particle moving to the left? When is particle moving to the right? When is particle standing still? So when you want to talk about the particle moving left or right, you're really looking at the velocity. You're looking at the slope of this, right? So a bit of a hint here that you might want to write down is if you're looking for the particle moving left, you're looking for a negative slope. You're looking for the velocity, which is the slope in this case. If you're looking for when the particle is moving right, you're looking for a positive slope. So when is the particle standing still? Obviously, that's the only thing left, is when you have 0 slope. Slope equals 0. Okay, so let's take a quick look. All right, so again, it's easier to look at this imagining a number line, right? So you have a positive slope, you're moving to the right, and then your negative slope, you come back, and then you stand still when you make your change. So you go right, stop, come back, make change, stop, come back, and go on. So when is this, looking at this graph of s of t, it is standing still here because the slope is 0. Then it's a negative slope coming down, so it is moving to the left, and then it's moving to the right again, and then standing still. Okay, so now I kind of have the arrows to help me see the direction. So moving to the left, I'm looking for a negative slope. It is a negative slope between 2 and 4. Remember, these are intervals, all right? If you don't like this way, it is okay to write it in this case. You can write that t is between 2 and 4. Don't include the ends, right? Do not include the 2 and the 4 because the particle is really not positive or negative at those two ends, right? So you don't want to include the end, so you want to have less than, not less than, equal to, okay? When is the particle moving to the right? Well, at 4, between 4 and 6, right? When was the particle standing still? Well, at the beginning, up till 2, and then again, picking up at 6, going to 7, okay? None of these are inclusive because at these, the ends, we don't know what's happening there, right? So the particle is pausing. So when you really want to talk about it, you want to just have these endpoints not be included in your intervals, okay? All right, next is my attempt, well, actually the book's attempt to connect this with econ, but it's the best we can do. So it says, part A, find the average cost of producing 100 washing machines. So this is this formula, C of X is the cost of producing washing machines, right? So average cost is the same as average slope, average speed, which is average change in speed. Sorry, let me back that up. Average cost is equal to slope. It's like the average rate of change, right? So same idea. So in part A here, you're looking for the average. So you're looking for between 0 to 100 washing machines, right? Because that's the average of those washing machines. So what you need to do first is find the cost of 100 washing machines and find the cost of 0 washing machines, right? 0 is actually very easy to calculate. Plug in 0, you get 200. That's right, 2,000. Plug in 100, you get 2,000 plus 100 times 100. So how many zeros there? 10,000 minus 0.1 times 10,000, right? So that would be 2,000 plus 10,000 minus 1,000. So that would be 11,000, right? So the average cost would be Y2 minus Y1. You have your Y2, right? You have your Y2, which is 11,000, and your Y1 is 2,000. So your average cost will be 11,000 minus 2,000, that's Y2 minus Y1, over X2 minus X1, which is 9,000 over 100. So average cost is $90 per machine, right? So if you produce 100 of these, the average cost is about $90 per machine. Okay. So find the marginal cost when 100 machines are produced. So I had to look this up. Marginal cost is the change in total cost when the quantity produced changes by 1 unit. So if we translate that into math, into calculus, it's the derivative. It's the derivative. It's how fast the cost is changing at when 100 machines are produced. Because, you probably know this, when you're mass producing something, the more you produce, technically you're supposed to save money as you produce more. But sometimes that's not the case because of a lot of other factors, right? So that's why this equation has 2,000 plus 100x minus 0.1x squared. I would assume 2,000 is like the base cost of like renting the warehouse and having your machines, buying the machines in the first place, right? So this is how you would go ahead and figure out, right, the marginal cost, so that at that moment of producing 100 washing machines, how is your cost changing at that point, all right? So we're going to go ahead and look at what we're used to, which is the calculus part of this. So go ahead and look at marginal cost. So we're taking C prime. So the derivative of C prime equals 2,000 is gone. You get 100 minus 0.1 times 2, so 0.2x. So the marginal cost of 100 machines is C prime of 100, which is 100 minus 0.2 times 100. That's 100 minus 20. So that's $80 per machine. So if the average cost is $90 per machine, but then at the instant of 100 machines is $80, that means that the cost was going down, was decreasing as we go, right? Because at the moment of 100 machines, it was only $80 per machine. But if the average is 90, that means somehow the cost was way more than 80 to bring that average up. So again, it should make sense that when you're producing 1 or 2, you're really not making much money. The cost is really high to not make it worth it. But as you produce more and more and more, then your cost is actually coming down. So then it says part C, show that the marginal cost when 100 machines 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 has made by calculating the latter cost directly. What this is trying to show you is that at a certain point, creating more is not going to help you. Creating more is not going to make your cost go down, right? It's going to plateau out. So in the beginning, the cost is really high and you're trying to bring that cost down, but then eventually that cost is going to plateau and flatten out because it's not worth it to produce more. So how do we know that, right? How do we know that? We are going to look at the marginal cost of comparing the marginal cost. So we're going to figure out how much is it when you're looking at the first one, after the first 100 machines has made. So you are looking at the cost of the 101 machine, the next one, 101, right? So the cost of producing 101 machines, I'm going to plug it into my original equation, is 2,000 plus 100 times 101 minus 0.1 times 101 squared. And no, I'm going to be honest with you, I don't calculate this by hand. So the answer was 11,079.9, right? But that's not the cost of producing the 101th machine. This is the cost of creating 101 machines in total. So you got to take away, you got to subtract the cost of 100, right? Which is what we got in part A. So the cost of 101th, I don't know the correct term for this, machine is 11,079.9 minus 11,000, which is 79.9, right? So it's $79.90. Now, compare that to the average cost. The average cost, the instantaneous cost was $80. So making that 100th machine didn't really make my cost go down that much. It went down by 10 cents. So what this is helping you do is see that, okay, well, after 100, then there's no true benefit to creating more than 100. So, maybe at this one warehouse, you want to create 100, and in the next warehouse, you want to create 100. That's kind of your cap to make it worthwhile, okay? All right. Last one here is back to physics. It says finding speed. A body's velocity is given at v of t. Find the body's speed each time the acceleration is 0. Okay, so again, you got to keep in mind the relationships here. For the position, that's s of t. Velocity is v of t, which is s prime of t. Acceleration is a of t, which is the first derivative of v, but also the second derivative of s. All right, so that's the relationship there. Now, speed, don't forget, speed is the absolute value of v of t, right? So speed has no direction. So whatever velocity I get, I just make sure I get the absolute value of it. I get the positive value of it. So you have to read the problem. Find the body's speed each time the acceleration is 0. So this is what you want to focus. When is acceleration 0? Okay, I am given v of t. So based on my relationship chart here, to get acceleration, I need to take one more derivative because I already have v. I want one more derivative, v prime, to get acceleration. So acceleration is 6t squared minus 18t plus 12. All right, the 5, this is meter per second. This is a unit, it's not variable. Okay, it says when x acceleration 0, so this is 0, so set this equal to 0. So you're solving for t, you're trying to find out what time does this happen? When does this happen? Factor out of 6, make your life a little easier. So, and divide by 6 on both sides, you get t squared minus 3t plus 2. If you factor, you get t minus 2, t minus 1, so equals 0. T is 1 and 2 seconds. So at 1 second and 2 second, acceleration is 0. Okay, so we found when. We found when this is happening. So now we take the when and plug it into to find the speed, right? So you want to say, well, at t equals 1, your velocity is 2 times 1 cubed, or plugging it back to velocity because velocity is speed, right? So plug that in, you get minus 9 times 1 squared plus 12 times 1 minus 5. So that's 2 minus 9 plus 12 minus 5. That gives me negative 7 plus 12, that's 5 minus 5. Oh, it gives me 0. So I get 0 minutes meters per second. Sorry, I'm trying to figure out my unit here. So at t equals 1, my speed is 0 meters per second, which is fine. It means it's not moving, right? That's okay. Again, for speed, it's absolute value, so I don't need to worry about it because 0 is not negative. So at t equals 2, plugging in the v equals 2 times 2 cubed, that's 8, minus 9 times 4, plus 12 times 2, minus 5. So that's 16, minus 36, plus 24, minus 5. So 16 minus 36 plus 24 minus 5, I get a -1. So I get -1 meters per second. That's velocity. Since I want speed, I want the absolute value of it. So the speed is 1 meter per second. Right. So now you've answered the question, the body's speed when your acceleration is 0. Okay. Make sure you do put a star on number 5. I guarantee you'll see something like this again in future assessments. Okay. All right. That's it, guys.